Hey guys, I'm going to make a video where I'd like to talk a little bit about basically how to build a really simple projectile system for Warsmash. Someone was asking me to kind of review the mathematics behind it. And as a rule of thumb for Warsmash, other than the 3D graphical engine, which they said they used from the role-playing strategy game that preceded Warcraft 3, the Warcraft 3 game was coded in like 3 months by a bunch of guys who were just Warcraft 2 programmers. And so they didn't do any three-dimensional math, and if you feel like you need to do three-dimensional math in Warcraft 3, you're probably doing it wrong. And I think that's even, we could extend that same proof of theoretical theorem idea to Warsmash. So let's start ourselves a little document here called Projectile Mathematics, right? And we're going to try to keep it simple, right? As much as possible, because in general, that's probably what the guys were doing in 2002. You don't really want it to be really complicated. So let's think about our projectile mathematics, right? What are we going to do? Okay, we're going to have something that floats through the air, right? It's like basically we're going to have like, the little wolfie over here with Thrall on it. Right? Here's like this little wolf, and it's going to have Thrall sitting on it. I guess Thrall should be green. I thought there used to be a way that I could get the colors while hiding everything else, but it doesn't seem to be something that I could do in this program anymore. Yeah, so we're going to go over here. We're going to get green. We'll go back here. Can we get... Oh, yeah, that's how you do it. Okay, there you go. So I can do that, and I can get green, basically, and we'll put Thrall in there. That's great. I was just making sure, you can tell it's Thrall, and he's going to have, like, a Doom Hammer right here. So this is Thrall, and somewhere else there's a hay barrel, and Thrall's going to throw lightning at the hay barrel, right? And the hay barrel, maybe it's one of those ones with the little target on it, so like, okay, that's where we're throwing the lightning. And he's going to throw this little lightning ball that, it has kind of like this sort of shape to it with little static around it. And this lightning ball, it's going to move from Thrall. It's going to start over here, and it's going to doop, 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 and it's going to go over to that hay barrel, and it is going to end there. And when we're dealing with that, right, we're going to be thinking about this in a mathematical two-dimensional space. The theory of Warcraft 3 in the two-dimensional space is that it was probably coded really fast. So basically, we're going to have X and Y, and it's going to be exactly the same as math class, because that's how Warcraft 3 was done. And so, you can sort of trace the idea of this line. We can use blue for the lightning. The idea of this line from Thrall to the target. Right? Now, one of the first things is, if you want to do homing, then each frame, we're going to move this lightning ball forward to the target, and it's going to be moving in an arc. But the height of the arc is actually pretty much irrelevant. If you think about what would need to be synced in the network code, it's really just the X and Y, so that you know the arrival time. I don't think you probably care about the height at all, so we'll do the height as the second step. But before we do that, we're just gonna talk about the lightning ball and its path along the ground. Right, and so to get the lightning ball's path along the ground, we could first say here that Thrall is going to be at a point Tx and Ty. Does that seem reasonable? And actually, let's not use T. Let's use S. Okay, and that way we can use T for target. It makes a lot of sense to me to say the target is Tx, Ty over here. So these are our 2 points. They each have an X and a Y. And we're going to be tracing a line between them with our magic lightning ball, and then we're going to move the lightning ball in an arc above them, right? So each frame, this lightning ball moves a little step across this, and you can think of this as a triangle, really almost like a right triangle, right? So in this right triangle, essentially, we're going to have dx, the distance x that we need to go, and dy, the distance y that we need to go. And if you can actually just add dx and add dy, you don't really need to worry about the third one. You can just sort of think about them in their own space there. But you need to know how far to go, right? So in Warsmash, initially people said the Warcraft 3 clock that's network synced updates about, I think it was 20 times per second. I tried doing that and it actually looked really bad because 20 times per second updating just doesn't look good graphically, right? So I'm sure what Warcraft must be doing is each tick of this 20 times per second thing, it moves a long distance, and then there's like intermittent ticks where it interpolates or something. So I didn't want to code that much. This is too complicated. Like I said, it's supposed to be something you can do in 3 months, code Warcraft 3. So I just changed my clock so it updates 60 times per second, which means that Warsmash is going to have problems when I try to network sync it. I don't care about that though, and today I'll probably end the video where I'll try to do this in Warsmash. And when I do, let's just do a clock that's 60 times per second. It's easy, straightforward, and works great locally. So given that we're going to be doing that, we want to talk about how far is this dx dy triangle, right? So this is like how far. Maybe this is our first question, right? How far on the ground? And in order to answer this question, right, what you want to do is solve for dx and dy, right? Because if you can do that, then you can add them to this point here, which we could call mx, my, which are just where we previously were, like my x, my y, basically, like where we started the lightning bolt each time we move forward. So my theory about, because you're going to create this lightning bolt, there'll be some kind of create function, and each tick you can just go doop, 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 doop in that direction. So my theory is that I think this is pretty straightforward math because we know the speed, right? So each unit has 2 attacks, and each attack has a projectile speed. So at the point that I'll be coding this in Warsmash, we're going to have just a function on the unit that is get projectile 1 attack speed, or get attack 1 projectile speed, get attack 2 projectile speed, right? So let's just assume everything's attack 1, makes it simpler. So we could even just call this PS for projectile speed. And yeah, this would be, so we're going to have variables, right? And the variables that we're going to have are PS, which is projectile speed, and then we have SX, SY, TX, TY. Basically, you can think of this as a point, SX, SY, which is source point. And really, you don't really need SX and SY and MX and MY both, right? So you could initialize MX, MY equal to SX, SY, and from there, you could just kind of think of where you are. So maybe we could even just use, should we just erase S? Should we, like, the thrall shouldn't be S anymore, and we'll just say start is now actually like start of the missile, right? It's a little bit simpler that way. So this is like the source point where the missile is starting, and we're going to have TX and TY, and this is going to be target point. And yes, for those of you interested, I agree this C doesn't look quite like a C. Okay, so we have SX, SY, TX, TY, and we want to solve for dx, dy. So solution, right? Solution. What are we going to do for this one? Dx, let's start with dx, right? Dx is going to equal something, which what I would say you want to do first is imagine the distance you were going was a distance of 1. It's not, but imagine it was, right? You could even call this d1x and d1y. And this could be 2 points, or like 2 sides of a triangle. And in this triangle, this is a special triangle, the distance is 1 that you're going, right? And so this down here is d1x, and this down here is d1y. If you think about going a distance of 1, we call that a unit vector in mathematics, right? You could figure out pretty easily how far that would be by just taking, sort of extend this guy out and figure out what is this whole difference. This is a right triangle also. This difference, tx minus sx. So this right here, tx minus sx. And you say, what is that thing divided by the hypotenuse, right? But in order to do that, you need this sort of hypotenuse of this triangle that is not 1. So there's a bigger triangle, right? And in this bigger triangle, we know that this is sx minus tx, tx minus sx, whatever I wrote above. Tx minus sx, right? Tx minus x. By the same logic, this side is actually ty minus sy, right? And it's just like, height minus height. So this one over here is ty minus sy. And so the key is something they teach kids to memorize in, I think for me when I was in middle school, is that if you have a triangle and it has this special property that it has a right angle and the sides are a, b, and c, and if you need to know how long c is, well, you can solve for the fact that c squared equals a squared plus b squared. Or I guess they usually would write it slightly more logical fashion, a squared plus b squared equals c squared, right? So, logically it follows if you take the square root of both sides, so maybe if we write it again, square root of a squared plus b squared equals square root of c squared, that the square root of c squared would just be the absolute value of c, which in general is pretty much just c. So in our cases, because we don't care about the negative. It is true, if you were in math class, you care about the negative. But so this means that c really equals like the plus or minus square root of this thing, and we're just only caring about the positive one. So that tells us, because it's a triangle, because all the sides have non-negative length, the value of c right here is the square root of a squared plus b squared. That's great, because that means that we know that c in our case, right, is going to actually equal the square root of tx minus sx squared plus ty minus sy squared. That's great. That gets us this distance. What are we going to do with that distance, right? Why did I care about that if this is c? Well, it turns out you want to know d1x, right? All you need to do is take tx minus sx over c. So I think it would follow that you could just say, sorry, I got to make my pen load here. D1x actually equals tx minus sx divided by, let's do a nice flat line, square root of tx minus sx squared plus ty minus sy squared. Right? And this would get you, this divided by that, it normalizes it. This is what we call normalizing a vector. This would be d1x and d1y by the same logic. Would be the square root of, maybe we'll make this a little bit taller, ty minus sy. Sorry, that's wrong. Bad square root. Square root is in the denominator because that's c. Tx minus sx squared plus ty minus sy squared. Now this looks really ugly, so let's review for a second. Why is it that, right? So if I have this little tiny triangle, and I know that then I have a really big triangle, and this has like a distance of 3, a distance of 4, let's say hundreds. They're 100, 300, 400. This is a 500 distance, right? And really, what I want this to be is one distance, but I want the same triangle, like the same relative amount in each direction, right? You can math out this, that like this one is 3 over 5 and this one is 4 over 5, right? Because of this idea. So it's just, I'm generalizing that same concept, having solved for the long side. That I want this little triangle. And then you're going to ask yourself, why do I want this little triangle? Well, I want this little triangle because if I know that little triangle, then I can say all my dx is going to be, it's going to be d1x down here that we just solved for, this side of this guy, with the extra added characterization that as well as d1x, you then can say, d1x would be if we were only going a distance of 1. But we're not going a distance of 1. We're going to go a distance based on projectile speed, right? But projectile speed in Warcraft 3, if it's specified to be 600, then you don't actually want to go a distance of 600. You want to go a distance such that after 1 second, you've traveled a distance of 600. So what you want to do is take 600 and say, how many updates do I make in a second? I make 60 updates in a second. Well, then we'll divide 600 into 60 pieces, and we'll each update will do that piece, and at the end of the second, we'll go the whole 600. So for that, what we're going to do is projectile speed divided by 60, right? I think that should be pretty straightforward. d1x times projectile speed over 60. So if you're in a computer, you don't ever want to compute anything twice, so you would want to actually factor this out, basically, and actually call, you want a name for tx minus sx. So, and ty minus sy, which is why we would call those, we already used the name dx and dy, but we could probably call it like, what do you think? I'm trying to think of a name for that, TS, or like DTS? Let's call it DTS, right? If you call it DTS, so suddenly this triangle here, this is actually DTS equals, or DTSX equals that, and DTSY equals this. DTSY equals TY minus SY. It's just going to simplify what you'll be typing in the computer, right? Because really, then your code is going to look like DTSX equals TX minus SX, DTSY equals TY minus SY, C equals square root of DTSX squared plus DTSY squared. And then you can effectively compute d1x, right? So like d1x equals, it's really simple, right? It's just dtsx over c. So your computer code is going to be dtsx divided by c, d1y, dtsy divided by c. So there's another way you can do this with sine and cosine, and it also becomes a question of what is faster, square root or sine and cosine. If the sine and cosine is faster, you might want to end up doing it that way. I hadn't really thought of that. Let's research that online a little bit. Never hurts to do a little research. Hey, open Chrome. Okay, great. Yeah. Sine versus square root performance. Well, this is not equivalent. Where's his results? Okay, here's his results. So he's saying the square root is faster than sine and cosine. I didn't know that. I hope he's right, because we're doing square root today. I was thinking there's another way to do it with sine. Let's not do that. Let's do the square root way. Great. So we pretty much solve for d1x, d1y, and this gives us the ability to say dx equals d1x times ps divided by 60, and dy equals d1y times ps divided by 60. And this right here, I think, is all you need to figure out your ground distance, your x and your y, right? Because once you know dx and dy, these two values here, you should be able in your code to basically say something to the effect of sx equals sx plus dx, right? And sy equals sy plus dy. And the whole idea is that we're just stepping forward every frame, and we're stepping forward in the x and we're stepping forward in the y, and we're doing it this way so that it's relative to our projectile speed along the ground. Now, if someone tells you that you want the projectile speed to be impacted by the curvature, and I don't know if Warcraft 3 does this. You might want to research if Warcraft 3 does this, right? Does a really fast projectile with a bigger arc take a longer time to arrive? I highly doubt that Warcraft 3 implements that, to be totally honest with you. Sorry, it looks like my mic got shifted there. I highly doubt that Warcraft 3 implements that. It's possible, but I don't think so, right? So if I have two projectiles going to the same point, one of them has a huge arc and one has 0 arc, but they have the same speed, I bet they arrive at the same time. I really doubt that the people making Warcraft 3 bothered to do the complex mathematics to say, oh, well, this one's tilted up, so, its lateral ground distance should be a lot less. I doubt it. I just really doubt it. And this gives you the ability to just basically say, okay, boom, here's my SX, SY. We just add a bit, add a bit, add a bit every frame. So that's your ground distance, right? We sort of have this idea of X and Y, and, we're just going to be adding, chunk every frame to our ground distance. But over top of this, there is the third dimension that is your height. And so I think the key is to think about your third dimension is Z, but let's think about this thing that we could call basically time as we travel, right? And what we want is that this is some kind of function that makes a parabola, right? So what do we know about parabolas? I think what we know about parabolas, first off, is that if you want to make a parabola, they probably teach you this in math class, you can use y equals x squared. It's a great function, makes an upward facing parabola, right? Just the same as how y equals x makes a line like that, line through the center like that. It equally follows that y equals x squared makes this nice parabola. So what you want to do is put that upside down, right? How would you put that upside down? Well, think about it. Y equals negative x squared. What does that give you? That gives you the exact same thing, except it's upside down, right? That makes total sense. And this is on an XY scale because that's what they teach you in math class. But actually what we're going to be doing is a time height scale. So of course this actually would be z equals negative t squared. But the difference there is pretty irrelevant. So now the question is, this still is not your parabola. This is an underground parabola. That's unacceptable, right? So you don't want an underground parabola. Okay. You want a parabola that goes over top of the ground. How are you going to do that? Well, turns out z equals this thing plus some number, like if you do plus 1, right? Then if you assume like this right here is 1, 1, 1, 1, 2, 2, 2, right? Okay, I'll put the 2 and the 1 on the same side, right? I mean, if you have some semblance of scale here, right? If I add 1 to my parabola, and 1 squared is 1, so it ends up here, right? You get the same parabola, but it's in the air a little bit, right? So that's pretty much what you want, and then just only range it from 1 to, negative 1 to 1. Sorry, this is negative 1. Negative 1 to 1, right? So you can just basically do an upside down parabola, and that's going to get you the same thing. But the key is you probably also want to stretch your parabola, right? So how do you stretch your parabola? And you can't just add 1 to the height. You really want to add some amount to the height. So in Warcraft 3, you have an arc. We could call this PA. I know on the Archer, they do 0.15. I always kind of wondered how those were implemented, but I know people disagree about what's the most effective way to make an arc that you could put on a projectile that you shoot. I always thought, and I could be wrong, I always thought that a projectile arc of 0.15 meant that if I was going from S to T, and this was the line that I was traveling, that then the upward distance in the center of my curvature, right? If this is my my curved parabola, right? I always thought that 0.15 meant that this thing was 15% of the total distance, right? So this is like 15% of whatever, s minus t or t minus s here, this distance, right? I don't know if that's actually true. I just always assume that's probably what they were doing because I didn't really know what else it was. So I was kind of thinking, what if we just do that in our example? And we might find out that that's wrong. But if it is, we'll change it and we'll do something different. Because I know it definitely seemed to be the case for me in Warcraft 3 that if I had a point S and T like that, and I set it to 1, that it goes up really far. Like whatever the units are here in Warcraft 3, it's close to my approximation that I thought, and I've always kind of assumed it was, which is where like this right here, now if my arc equals 1, if my projectile arc equals 1.0, that then this thing has a value of t minus s. But I guess it's the magnitude of the vector of t minus s, right? Because it's not relative to like tx or ty, it's just the distance along that line. So that was a vector magnitude notation for math class. I don't know if you ever had those classes. So that's kind of my thought process here. I think what we want to do is have our parabola peak at projectile arc, whatever that number is, times the distance we're traveling. And I just think that's how I'm going to do it. You know, maybe if I find out Warcraft's different than that, I could change. But that just, to me, that's a pretty straightforward way to do it. And it's in keeping with how Warcraft 3 functioned as far as I know. You know, feel free to prove me differently. So, on that basis, now we have this whole parabola thing here, right? But it's not quite going to be this easy because we might want to stretch it, right? Maybe we want to say, well, okay, so first off, my parabola that I had just drawn, you know, it has these little ticks along here. I guess we'll see if we can keep this flat along that line. You know, we're going to draw this parabola, and we want it to be the case that maybe it's stretched out. You know, maybe it's a parabola from here to there, right? What would be the math to get that? You ever ask yourself that question? Well, to stretch it out wider, right, all you need to do in the equation that we had, which was, in this case, z equals negative t squared, is that, you know, we added, maybe we add 2, negative t squared plus 2. Z equals negative t squared plus 2 is not this graph, by the way, right? It's more like that. It's not widened. In order to widen it, all you have to do is take your thing that you're squaring, your t in there, right? Okay, that broke a little bit more than I thought it would. We have this thing that we're squaring, right? And the thing that we're squaring, it used to be t, but if I say that instead it's going to be 1/4 of t, right? Then when t is 4, it's 1. Which means that in my original example, where, and this is actually mathematically accurate, right? That z equals negative t squared plus 1 would look like this, and it intersects the x-axis at negative 1 and 1. Then it would follow that this guy would intersect at negative 4 and 4 because I've multiplied t by 1/4. So it's sort of 1/4 is inclined, right? So doing that is great. And you can get your height by adding it as on the end here is just this constant factor. What that doesn't exactly tell you is how do you shift it to the left or the right, right? So the way to shift it to the left or the right is pretty much that we just take whatever t is in this example, and we want to say don't actually use t. Like right here, okay, t minus 4, t plus 4. Don't actually use t. Use t minus something, right? Suppose I use t minus 4. So suddenly my equation becomes z equals negative, this is a 1/4, and then I insert in here t minus 4, right? And I'm going to put these parentheses in the right place because that's really important. T minus 4. By inserting that t minus 4, you're essentially taking this same graph, but you're saying, whenever I try to find a point, like I say, okay, this, you know, what is this height as a function of t? If this is t and this is, then the height is z. That height as a function of t now is a function of t minus 4, which means that at 0, it's going to be what was previously the output over there. So that means if you kind of math that out in your head, and this takes a little bit of intuition to see this, but if you think about what that basically means, right? It's that now at 0 you evaluate what we previously had at minus 4, so you have a point right there. And at 4 you evaluate what we previously had at 0, right? So that's going to be right here. That's going to be the 2. And then at 8 you're evaluating what we previously had at 4, right? It's just 8 minus 4. So that's going to get you your point out here. And so this gets you a parabola that's going to actually curve just right like that. And it runs from 0 to whatever number based on how much you curvature it, right? So to me, this seems like a pretty straightforward way that I can say if I know how long my projectile is going up and back down, right? If I have a 600 projectile speed, right now if we assume this right here is going to be a 600 projectile speed, and that this thing here is going to be distance times, well actually it's not 600, I kind of want it to be that, but it isn't really. I suppose it would be the end point minus the start point, kind of like I was saying with the whole vector magnitude. So if that's true, then the equation for your height, given the number of steps, the time that you've stepped forward, right, would pretty much be something like this, but instead of like 4 and stuff, we have to input real, what are our variables, right? So our height, we know we can compute based on our starting distance. We can say, okay, what's our height going to be? And that's just height, So basically, right, from what we said earlier, height is going to equal projectile arc times, projectile arc times the vector magnitude of t minus s, which looks fancy, but it really, really isn't. It's distance to target, right? You could even just call this distance, maybe PA times distance. So that's our height. And now the other key is, is that right? The reason that that isn't right is because I made the assumption, basically I was trying to claim that this would give us 1 and minus 1 as points, and it doesn't, even as far back as if you change this to minus t squared plus 1. So I was a little bit wrong, actually. Here's why I'm wrong. If we go back to this point when I said z equals minus t squared plus 1, my oversight is what happens if you put 2 in here instead of 1, right? If you do that, then this thing no longer intersects the ground at 1 and minus 1. So the key is you want to actually change the amount of curvature in your arc that you have. So if you actually wanted it to be that way, right? If you wanted it to be that you had 1 and minus 1 and 2 as a point, and you actually made a parabola out of these points. In order to do that, your equation would have to be z equals minus t squared, this guy divided by 2, I think, plus 2. Right? That's actually wrong. It's actually not divided by 2. I think it's times 2. So I guess does that seem right? Yeah. Because we used to subtract 1 when we get to this point. Now we're subtracting 2. So it's this thing times 2. So it's really just the whole thing we had. Maybe that kind of makes sense, I guess. Times 2. That we're just stretching it vertically, so our output is being multiplied. So that is just times 2. So what this gets back to is I made the incorrect assumption here when I did this 1/4 t plus 2. If you put this in a calculator, it won't be what I thought it was. That's because I was basically doing 1/4 t plus 1. I should have then multiplied all of that by 2 on the outside. And this is wrong, right? So you get the same thing here, plus 1, all that times 2. Which also should let us apply that here, because then it isn't plus height. Then that's wrong. It's actually plus 1, and you wrap that in parentheses and multiply by height. And that'll make that a lot more logical. Then on the inside here, we get back to our squared component, right? The squared component, if you know your travel distance, right, t minus s, which we can just call distance. We're calling that one distance. Then I guess, really, I did a lot of stuff with 4, which is just half distance, really. So pretty much, let's say half equals distance. This is kind of like what you'd put in the computer, right? Distance divided by 2. So then what I can do is 1 over half times t minus half. And this would be a valid equation if t was in the correct units, right? Now then your question is t in the correct units. Because I was assuming that t is in units that runs from 0 to distance, which it might not, right? It might not. But for initial assumptions, we could say it probably does. And let's see if the math works out. So I think what we're going to do next is we're going to try plugging this into Warsmash and just see what we get. See if we can get a parabola that looks half decent based on some really basic math here. I think obviously it doesn't exactly look pretty, but we didn't really do anything that's immensely complicated. Yeah, so I'll get back to you on that with some Warsmash.